Hi everyone, how's it going today? I just wanted to welcome everybody to our first Western Canada Regulator webinar. We're proud to have Kayla here from Swagelok to do the presentation today. He's just getting contacted in with us right now. So what the plan is for today is the webinar will be approximately 30 to 40 minutes. We're going to run through the slideshow, and then there'll be Q&A time after that. If you do have a question for us, for Eric, if you could send that to me in the chat field, and therefore I can get it and I'll read them over to Eric at the end of the slideshow. No question is a wrong question, so please feel free to send them through. We'll just request that you guys stay muted throughout the presentation, and then that way there won't be any feedback issues or things like that.
Well, good morning, everybody. As James said, my name is Eric Kayla. I'm the field engineer for the western portion of North America. And today we're going to have an introduction to pressure-reducing regulator theory and operation. So our agenda today, we're going to be talking about the operating principle of pressure-reducing regulators, which all revolves around a balance of forces. The next thing we're going to talk about are the different sensing elements that are available in the pressure-reducing regulators. We're going to talk about hard seat versus soft seat designs. We're going to cover a couple different loading mechanisms. And then throughout the presentation and at the end, we're going to cover some terms that you'll need to know when talking about pressure-reducing regulators. So a pressure-reducing regulator is intended to take a high inlet pressure, reduce that to a desired set outlet pressure, and keep that outlet pressure constant, regardless of changes to the inlet pressure or changes to the flow and the demand of the fluid downstream. So as we look inside of a regulator, we can break it out into three different areas. The top portion of the regulator is the loading portion of the regulator. In the case shown here, we have a spring-loaded regulator. The middle part of the regulator is the sensing element. And the sensing element can either be diaphragm sensing or piston sensing. And this is kind of the area where we have that balance of forces operating around. And the lower portion of the regulator is our internal forces. So we've got some pressure forces, some spring forces with that small spring below the poppet that all, again, operate in that balance of forces. Now, as we talk about the balance of forces, you can really think of the regulator as a seesaw. It's kind of the seesaw that you played with on the playground as a child. The balancing point in the middle of the seesaw being the sensing element, and on either end of the sensing element, you're going to have on one side your loading forces, and that's your, in the case of a spring-loaded regulator, the spring-loaded force, and on the other end are going to be your internal forces. So your internal pressures, your outlet pressures, and so forth. If we break this out into a balance of forces, the first force you see is your loading force, and that's going to be on top of the sensing element. The next force is going to be your inlet spring force, and that's that small spring that keeps our poppet seated into the seat of the regulator. The next force that pops up is going to be our outlet pressure forces. This is that lower pressure that operates on that large sensing diameter. And lastly, we have our high inlet pressure force acting on the small area of the poppet. So as we push all of this out into a formula, we have our loading force F1 equal to the sum of our internal forces, F2 plus F3 plus F4. As we look at the different types of sensing elements, we really have two choices. We can have a diaphragm sensing regulator, or we can have a piston sensing regulator. A diaphragm sensing regulator is going to be more sensitive. So as you have small changes in pressure in your system, your diaphragm is going to react more quickly and be more responsive to small variations. We do have a wide choice of materials available for the diaphragm. They can be metallic, they can be a non-rigid plastic like a PCTFE or a Teflon, or they can be any number of different elastomers. A piston sensing regulator is for higher outlet pressures, but it's going to be less sensitive to small fluctuations in your system pressure than a diaphragm. So it's good for, again, higher pressure applications, or maybe applications where you have a regulator somewhat shortly after a piece of reciprocating equipment, maybe a compressor or a pump, where you're going to get those small, tiny fluctuations in pressure coming from that piece of equipment that over time may weaken and end up rupturing a diaphragm, a piston sensing regulator is a much better option for that type of application. So again, it is less sensitive, and we do have some options for O-rings and stuff just to make it compatible with the rest of the system. The next thing we're going to talk about is hard seat versus soft seat design. A soft seat is going to be just an O-ring that's built into the poppet itself. So in the case shown here, we've got a two-piece poppet with the O-ring trapped between the two pieces of the poppet. And then we have a metallic machined seat. So we have this poppet that's going to stroke in and out of the seat, and as it comes close to closing, that soft elastomer is going to seat against the seat and help shut off the flow through the regulator. A soft seat design is very good for low pressure applications, and with the softness of that elastomer, you can overcome maybe some amount of contaminant in your system, or maybe overcome some damage to the seat. As we look at a hard seat design, you'll see that we have a single piece machined poppet that's going to be machined out of a metallic, typically stainless steel, and then our hard seat is going to be a harder plastic. It's going to be PCTFE or PEEK, and our poppet, as it strokes in and out of the seat, is going to mate up with the seat and shut off the regulator. So you can see with this harder seat design, it's going to be less forgiving for any contaminants in the system or any damage to the seat. So it's important as we talk about regulators to have good filtration before the regulator so that you don't have any issues with the seat and the poppet interacting together. And what this leads us to is the term creep. And creep is a slow building of outlet pressure caused by that high inlet pressure on the inlet side of the regulator. Regulators are not designed or built as shut-off devices. So over time, because you have a dynamic device and that poppet and seat configuration aren't necessarily built to shut off completely, over time you do have a little bit of seepage of high pressure to the low pressure side. So that terminology, we call that creep, and that's a good term to be aware of. If you do need your regulator to be a shut-off device, the best thing you can do is put a shut-off valve right before your regulator. Okay? The next thing we're going to talk about is loading mechanism. And the first type of loading mechanism is going to be a spring-loaded regulator. The second type of loading mechanism is going to be a dome-loaded regulator. So where we talked about a spring-loaded regulator where you compress the spring to generate the load on your sensing element, a dome-loaded regulator, we're going to apply a pressure into our loading area, a pressure above that sensing element to supply the load to the regulator. And the last type we're going to talk about is a combination spring and dome regulator. And basically in this case, our loading mechanism is going to be the combination of our spring load plus a fluid pressure in our dome. So the first thing to talk about is a spring-loaded regulator. And in the spring-loaded regulator, we have our spring force, that F sub S, above our sensing element. In this case, that sensing element is our dark black diaphragm then. And then below that, we have our internal forces now. So as we're shown in this case, our spring force is less than our internal forces. So our internal forces are pushing the sensing element up and keeping the poppet in the seat of the regulator, not allowing higher pressure to come across the seat to increase the pressure in the downstream side of the regulator. Once the spring force, in this case our loading force, exceeds the internal forces of the regulator, we can see that the spring force pushes the sensing element downward, pushing the poppet out of the seat, allowing that high pressure to come across the seat to increase the outlet pressure of the regulator. So we've got a couple different styles of spring-loaded pressure regulators shown here. We have the instrumentation style, which is a smaller, more point-of-use type of product. And then we have process-type spring-loaded regulators as well. These are going to be larger, 1-inch, 1.5-inch, 2-inch connections, whether they're a pipe connection or a flange connection, generally used for bulk delivery, whether that's a bulk gas delivery or a bulk liquid delivery, but definitely to control more of a process type of fluid system. All regulators are going to have a flow curve. So in the example shown here, we have spring-loaded regulator flow curves. And what you'll notice is, as flow increases from left to right across the bottom of our graph, our pressure on each of the flow curves drops off. So what this is as more flow is required through the regulator, our set pressure is going to tend to drop off. This phenomenon is called droop. And the formal definition, droop is a decrease in outlet pressure caused by an increase in flow through a pressure-reducing regulator. So you can see in the graph shown here, droop is pretty clearly demonstrated, that drop in set pressure as flow increases to the regulator. Moving on to dome-loaded regulators. In a dome-loaded regulator, we're basically replacing that spring as our loading mechanism, again with a pressurized fluid above our sensing element. So in the case here, we have our dome force, the F sub D, above our sensing element, and then we have our internal forces, F, below the sensing element. In the case shown in the picture on the screen now, our internal forces, F, are higher than our loading forces, F sub D, keeping the sensing element pushed upward and the poppet in the C. Once the fluid forces above the sensing element, our F sub D, exceeds our internal forces, F, we push the poppet out of the seat, allowing high pressure to come across the seat and raise the outlet pressure of the regulator. So as we look at a cutaway of a dome-loaded pressure regulator, we can kind of see it's a little bit more simplified than the spring-loaded regulator in that there's no mechanical components above our sensing element. The image on the left side of the screen shows a large dome-loaded pressure regulator, and then off to the side is a smaller pilot regulator. So in this case, we're taking a small slipstream off of our high-pressure inlet into our pilot regulator, reducing the pressure out of the pilot regulator into the dome, and that's how we're controlling our dome pressure. And our dome pressure is going to be the outlet pressure of the regulator. So as we look at kind of a schematic or diagram of this setup, we can see our red high-pressure fluid coming into our dome-loaded regulator and into our pilot regulator. And then once we reduce the pressure in the pilot regulator into that lower pressure, that green color, into the dome, then we see that same color is also the outlet pressure of the dome. So what we're noticing is that a dome-loaded regulator is basically a one-to-one relationship. Whatever the pressure is in our dome is going to be the outlet pressure of our regulator. Also in the case shown here is an outlet flow loop. In the outlet flow loop, you'll notice a symbol right before the outlet flow loop connects back into the downstream side. That's a small orifice fitting or a bleed fitting, which allows a small trickle flow to continually flow through the dome into the downstream side on the outlet side of the regulator. This gives us what we call dynamic control in the dome of the regulator. We can raise the pressure in the dome, and then we can reduce the pressure in the dome. If we didn't have that outlet flow loop, we wouldn't be able to drop the pressure in drop the pressure in the dome, and therefore drop the pressure downstream. We'd be able to continue to raise the pressure, but we wouldn't be able to drop it. There would be nowhere for that excess pressure, that excess fluid in the dome to vent to. So the outlet flow loop gives us dynamic control to that dome pressure. As we look at what this looks like on the back side of the regulator, we can see the fitting that is in the high pressure side. They've just got a male connector there that leads into the tubing into the pilot regulator. The key to this picture is to look at the fitting that's in the downstream side. And that fitting is actually going to be the bleed fitting. That's got the small orifice diameter inside of it that allows that trickle flow to the downstream side and gives us our dynamic control. So as we look at our flow curves, we'll see that the blue line is the one we're familiar with from the spring-loaded regulators. The blue is kind of our baseline. It's this typical flow curve from the spring-loaded regulator. The red line is the flow curve from a dome-loaded regulator. And you'll notice that we've gone closer to horizontal with that red line. We have the same starting point over on the left side of the graph and the same finishing point on the right side of the graph. So that's leading us to believe that we've got the same geometry in the regulator body, the same seat and poppet geometries and configuration, the same porting and so forth. But the differences in the flow curves itself are all a result of changes to our loading mechanism. So if keeping a more stable pressure across a wider flow range is important to you, consider a dome-loaded regulator over a spring-loaded regulator. Now, some options that we can do to change up the dome-loaded regulator and make them a little more responsive and improve the flow curve is to add external feedback options. So this first option is to add external feedback to the main regulator. So in this case, our sensing chamber is no longer sensing off the outlet of the regulator, but it's sensing off of a feedback line that is installed somewhere downstream of the regulator. Just like any device you put into a fluid system, whether it's a regulator or a valve or even an elbow, you're going to tend to have some drop in pressure for several diameters of your tubing or piping downstream from that device. So if you need more exact control, using external feedback to the dome-loaded regulator will give you a little bit more stable outlet pressure because now you're sensing off of the system that is further downstream and not subject to the pressure losses after the regulator. The second option is to take that same feedback point and instead of feeding it to the dome-loaded regulator, feed it to the pilot regulator. So now our dome-loaded regulator continues to sense off of its own outlet, but our pilot regulator is sensing off of several diameters downstream. And now our pilot regulator is adjusting the pressure into our dome to be more responsive to the pressure downstream that is important that we want to control to. So as we look again at our flow curves, now we have a green line and a purple line as well. That green line is going to be our external feedback options. So they're both pretty close. The external feedback to the main is going to be better than a standard dome-loaded regulator, but not quite as good as external feedback to your pilot regulator. The best case is going to be the purple line shown there, and that's going to be an electronic pilot regulator. So instead of using a purely mechanical system, now you're looking at installing pressure transducers, an electronic pilot regulator, and then some system control. And in that sort of case, you can keep your flow curve very close to horizontal throughout most of the flow range of the regulator. We have an example here of a large regulator, and in this case we're looking at, looks like about a 4-inch inlet and a 2-inch or 3-inch outlet. But you can see the plumbing from the external feedback to the pilot. So we've got that line, that connection in the downstream side, just below the downstream gauge, that feeds back and attaches to the middle of our pilot regulator. So if you see an example like this in the field, that's a dome-loaded regulator with external feedback to your pilot regulator. The last type of loading mechanism we want to talk about is a combination spring and dome-loaded regulator. And in this type of regulator, our loading force is going to be the sum of our spring force plus our dome pressure. So as we look at the cutaway, we see we have it's kind of a hybrid of both the dome-loaded and the spring-loaded. Our spring stack isn't quite as big as it is in our traditional spring-loaded regulator, and our dome-loaded chamber isn't quite as big as we would expect on our traditional dome-loaded regulator. And we also don't have the porting configuration to give us dynamic control in this type of regulator that we do in a normal dome-loaded regulator. The best way to describe how this type of regulator works is to kind of look at it in an application. So in this case, we've got a piece of rotating equipment that we're calling a pump that has some pressurized shaft seals. And we need to keep those shaft seals 15 psi higher than the pressure that's in the pump itself. So when the system is not running, we set the spring load in the regulator to 15 psi. So when the pump isn't running, we have 15 psi coming through the regulator to load those shaft seals to the 15 pounds that we need. Once the pump starts running and starts building pressure, then we're taking a small slipstream off of the pump outlet and pressurizing our dome chamber. So now we have our dome chamber is the same pressure that's in our pump plus the 15 pounds from the spring, giving our shaft seals 15 psi plus the pressure in the pump or in the dome. So in the example shown here, our pump's running at 100 psi plus the 15 psi from our spring. So our shaft seals are going to be pressurized to 115 psi, which is the 15 psi we want over the pump pressure. Now we want to talk about a few regulator terms that will be important to know as you look at different types of regulators and different regulators for your system. The first term to talk about is lockup. And as you're reducing flow, so you're going from right to left on your flow curve, as you're reducing flow and as you get very close to the zero flow condition, so you're almost on that zero axis on the flow side, you have a sudden increase in outlet pressure. And that's called lockup. So as you decrease flow to zero, right as you get to the zero flow condition, you have a little bit of a jump in pressure. And that is called lockup. The inverse of lockup is seat load drop. So as you start to flow through the regulator and you're starting the zero flow condition and moving off from there, you'll have a sudden decrease in pressure. And that's called seat load drop. So in both cases, we just want to be aware that these conditions exist and that we don't want to be operating our regulators very close to that zero flow condition or very close to a low flow condition where the regulator is not designed to operate. If you are operating in this area where you're going to be experiencing lockup and seat load drop, you're going to have very sporadic performance, and you probably aren't going to be pleased with the performance of the regulator. The third thing to talk about is supply pressure effect. And supply pressure effect is a change in our set pressure based on a change in the inlet pressure. And this typically occurs when a regulator is attached to a gas cylinder. And as the gas cylinder is depleted and the pressure goes down, we'll begin to see an increase in outlet pressure on our regulator, even though we haven't touched our regulator. And this all stems from our balance of forces. But the best way to talk about this is going to be to kind of demonstrate what's happening. And here we have a little point of use instrumentation regulator that we're just going to imagine has a supply pressure effect coefficient of 1%. So our effect on our outlet side is going to be 1% of the change on the inlet side. And they're always inverse. So if we have a decrease in inlet pressure, we're going to have an increase in outlet pressure. So in the case shown here, we've just started up our system. We've got new gas cylinders that are pressurized to 3,600 psi, and we have an outlet pressure of 50 psi. As we begin to use our gas and deplete the system, now our inlet pressure goes from 3,600 psi down to 2,600 psi. So we've lost 1,000 psi on our inlet side. 1% of that is 10 psi. So we'll see a 10 psi increase in the downstream pressure. And again, this is just from the balance of forces within the system. There's been no change to the loading on the regulator. As we continue to deplete our cylinder pressure, now we've gone from 3,600 down to 2,600 down to 1,600 psi. We've actually had a 2,000 psi decrease on the inlet side of our regulator. So we now have an increase of 20 psi on the outlet side. So we've gone from 50 psi to 70 psi. The important thing to be aware of here is that you will see a change on outlet pressure based on changes to inlet pressure. So be aware if you have sensitive equipment downstream or if you're going to set relief devices that they may be activated by changes in the inlet pressure. So the question comes, how do we manage supply pressure effect? And there's really two different options. And the first option is to have two-stage pressure reduction. This can be done in a two-stage pressure regulator, as shown there on the left-hand side. It's actually two regulators built into one body. Or on the right-hand side, we have two regulators in series. So in this case, our supply pressure effects are going to be multiplied. So if we imagine looking at the two regulators in series in that right-hand picture, if they both had a 1% supply pressure effect, we'd have 1% times 1%, and then end up giving us a 0.01% total supply pressure effect. But it's going to be actually in the same direction of the change in our inlet pressure because we've got the two regulators. The second thing we can do is modify the controlling mechanism. And the controlling mechanism is really the poppet and seat interaction. So we'll look at two different options here. You have a balanced poppet design or an unbalanced poppet design. And the balanced poppet, or the unbalanced poppet design, you have your high inlet pressure forces acting across all of the horizontal areas in the poppet, working to push that poppet back up into the seat. On a balanced poppet design, you have an orifice through the poppet that allows the lower outlet pressure to be below the poppet. So now your pressures on both sides of your poppet are balanced, and then you have just a little smaller area that the inlet pressure forces can act upon to push the poppet into the seat. So a balanced poppet reduces the total area that our high inlet pressure can act on. This gives us less sensitivity to supply pressure effects, and also reduces our seat load drop and lockup, so we can use a larger seat and get more flow through our regulator. So if you look at just kind of an example of a balanced poppet design on that larger cutaway picture, you can see the orifice machine through the poppet and allowing that lighter green color, our lower pressure, to be above and below the poppet, balancing the pressure forces on either side of the poppet. And then we just have that small area that the inlet pressure can act upon to push the poppet into the seat. Okay, so that kind of runs through just in a very brief overview to demonstrate what's happening. And here we have a little point of use instrumentation regulator that we're just going to imagine has a supply pressure effect coefficient of 1%. So our effect on our outlet side is going to be 1% of the change on the inlet side. And they're always inverse. So if we have a decrease in inlet pressure, we're going to have an increase in outlet pressure. So in the case shown here, we've just started up our system. We've got new gas cylinders that are pressurized to 3,600 psi, and we have an outlet pressure of 50 psi. As we begin to use our gas and deplete the system, now our inlet pressure goes from 3,600 psi down to 2,600 psi. So we've lost 1,000 psi on our inlet side. 1% of that is 10 psi. So we'll see a 10 psi increase in the downstream pressure. And again, this is just from the balance of forces within the system. There's been no change to the loading on the regulator. As we continue to deplete our cylinder pressure, now we've gone from 3,600 down to 2,600, down to 1,600 psi. We've actually had a 2,000 psi decrease on the inlet side of our regulator. So we now have an increase of 20 psi on the outlet side. So we've gone from 50 psi to 70 psi. The important thing to be aware of here is that you will see a change on outlet pressure based on changes to inlet pressure. So be aware if you have sensitive equipment downstream, or if you're going to set relief devices, that they may be activated by changes in the inlet pressure. So the question comes, how do we manage supply pressure effects? And there's really two different options. And the first option is to have two-stage pressure reduction. This can be done in a two-stage pressure regulator, as shown there on the left-hand side. It's actually two regulators built into one body. Or on the right-hand side, we have two regulators in series. So in this case, our supply pressure effects are going to be multiplied. So if we imagine looking at the two regulators in series in that right-hand picture, if they both had a 1% supply pressure effect, we'd have 1% times 1%, and then end up giving us a 0.01% total supply pressure effect. But it's going to be actually in the same direction of the change in our inlet pressure because we've got the two regulators. The second thing we can do is modify the controlling mechanism. And the controlling mechanism is really the poppet and seat interaction. So we'll look at two different options here. You have a balanced poppet design or an unbalanced poppet design. And the balanced poppet, or the unbalanced poppet design, you have your high inlet pressure forces acting across all of the horizontal areas in the poppet, working to push that poppet back up into the seat. On a balanced poppet design, you have an orifice through the poppet that allows the lower outlet pressure to be below the poppet. So now your pressures on both sides of your poppet are balanced, and then you have just a little smaller area that the inlet pressure forces can act upon to push the poppet into the seat. So a balanced poppet reduces the total area that our high inlet pressure can act on. This gives us less sensitivity to supply pressure effects, and also reduces our seat load drop and lockup, so we can use a larger seat and get more flow through our regulator. So if you look at just kind of an example of a balanced poppet design on that larger cutaway picture, you can see the orifice machine through the poppet and allowing that lighter green color, our lower pressure, to be above and below the poppet, balancing the pressure forces on either side of the poppet. And then we just have that small area that the inlet pressure can act upon to push the poppet into the seat. Okay, so that kind of runs through, just in a very brief overview, the theory and operation of a pressure-reducing regulator. At this point, we want to open the floor to any questions that maybe anybody may have, or any questions that have come during the presentation.
If you could send the questions over in the chat, that would be great, and then we can pose the questions to Eric. We do have a couple of questions that have come in so far. First one is, why does the RHPS regulators use a balanced valve? Isn't it the same as a two-stage regulator that the K-series uses?
Okay, good question. The balanced valve in the RHPS is actually the same as that balanced poppet we just talked about. So there are different terminologies depending on regions and so forth, and balanced poppet and balanced valve can be used interchangeably. So it's not the same as a two-stage regulator, but it is the same as the balanced poppet design. Good question.
We just had another one come in. It was, when can we expect a NACE vaporizing regulator, or is it in the future?
Wow, it's a good question. I don't know off the top of my head when that would be available. That's certainly something that I can look into and feed that information back to James. And then we can, James, I don't know if that's something we would want to post on the blog, or maybe just get the contact information for that particular question and get back to them directly.
Yeah, we can. We'll contact that person directly. That's no problem.
Okay.
We just had another question come in. Is the regulator, or can the regulator be used for two-phase flow?
Two-phase flow. Can it be used? Yes. Performance is going to be, it definitely won't be as planned or as demonstrated on our flow curve. So it'll take some testing in your system just to get the performance dialed in. And something to be aware of is if you've got a two-phase fluid going through a regulator, you will continue to change phases as you have that pressure drop through the regulator. So if it's important to keep the proper mixture of gas and liquid, you will end up having probably more gas on the outlet side of the regulator than you do on the inlet side.
We have another quick question here that says, can they be used for less than 15 PSI?
Less than 15 PSI?
Yeah, 15 PSI.
Okay, and if we're talking 15 PSI gauge pressure, then yes, there's a wide range of products available for that. But if we're talking 15 PSI absolute, then that's a special case of regulator called a sub-atmospheric regulator. And talking about Swagelok products, our K series and our RHPS series do not have sub-atmospheric options. We do not have a sub-atmospheric regulator in either of those product series, but we do have a sub-atmospheric regulator available in our HF regulator product line. Those are more of a higher purity instrument point of view sort of product.
Okay. We had another quick question. Will Swagelok be offering both the instrument and process regulators?
Yes. Both the process regulators and the instrument regulators are available now.
Could you discuss discuss relieving regulators? Any comments related to creep, perhaps?
Okay. So by relieving regulator, I believe that they're referring to a self-venting regulator. And what a self-venting regulator allows is you can actually raise and lower the pressure in the regulator without any demand downstream. It doesn't have a whole lot of effect on creep, but if you do have your outlet pressure rise above the point where the regulator was vent, then it would self-vent and allow some of that excess pressure out through the regulator.
Okay. We have another question here. What diaphragm is optimal for flow control at low pressures?
For flow control at lower pressures, you want to be looking at an elastomeric diaphragm, something that's going to be very soft and flexible. It's going to react to the small changes in pressure that you'll see in a low pressure system.
Okay. What are the benefits for using Teflon diaphragms over stainless steel diaphragms?
A Teflon diaphragm is going to be a little bit more flexible, so it'll react to smaller variations in pressure in your system. But you may, and I guess both stainless steel and Teflon are pretty compatible with most materials. So that would probably be the big benefit for Teflon is the flexibility. A stainless steel diaphragm might be a little bit more robust for quicker changes in the system, and they're both going to be subject to the if you have pressure vibrations, they're both going to be subject to work hardening and eventually cracking. So there's similarities in both of them. They both have the same failure mode as well.
All right, a couple more questions here. Is it important to keep regulators for general compressed air use lubricated, i.e., do we need an inline lubricator?
If your air is dry coming out of your compressor, you've got the clean, dry air, so to speak, then what you're going to do is you're going to dry out your soft goods in your regulator. So you'll dry out your elastomers, which will decrease the useful life of those elastomers in the regulator. So if you don't have a lubricator in your system, you're just going to need to replace your soft seals a little bit more frequently than you would if you did have a lubricator in the system.
Okay. Do we have regulators available that are electronically actuated based on a downstream transducer?
That's something that we can do. It's not going to be a catalog item. It's something that we'll work directly with the customer with to specify all the details for the system that we're going to be using. And so if you have a case like that, then contact your salesperson, and they'll probably contact me, and we'll work directly to get you the most optimal design for that system.
Perfect. What is the typical temperature rating? Can it be used for flow of steam?
Steam is not optimal for any of our regulator products at this point. And a lot of it is to be done with, a lot of it has to do with testing. We just haven't had any testing done in steam. So at this point, we can't say that any of the regulators are a good option for steam.
We do have a question here. Do you ever come to Canada to visit customers, or is it best for them to contact the sales rep and then us contact you? What's the optimal for you?
I do get to Canada quite a bit. I've been up there, I think about 10 times this year. So if if there is an opportunity for me to visit someone, then definitely work with your salesperson. They'll contact me, and we'll arrange for a visit sometime in the near future.
Perfect. Another one here, does ambient temperature changes affect the flow control from the outlet of the regulator? Or are certain diaphragms optimal for changing temperatures? For example, minus 20 C to positive 55 C.
Yeah, so what that's going to basically be is that supply pressure effect we talk about. So as you have temperature changes on a vessel like a gas cylinder, that does change the pressure in that cylinder. That as the pressure changes in that cylinder, it will affect the regulator, and you'll basically be experiencing supply pressure effect that we talked about.
On a rare occasion, a regulator may freeze to the point where it becomes a block of ice. What is the cause of this?
Good question. That is called the Joule-Thomson effect, or Joule-Thomson coefficient. And for most fluids, as you drop in pressure, you also drop in temperature. So what happens is as you have a high inlet pressure and drop it to a low outlet pressure, your gas or your liquid is also cooling as well. So that's what leads to that freezing of the regulator. It may or may not be a problem depending on your system. If it does freeze into a block of ice, then that's obviously an issue. So, yeah, to overcome that, the best thing to do is either do two-stage pressure drop and allow the fluid to come back up to a little warmer temperature before the second pressure reduction, or to preheat your fluid before going into the regulator.
Alrighty. Got another one here. In a shutoff valve, before the regulator application, can the sudden increase in pressure as a result of opening the valve damage the regulator? For example, 3,600 psi upstream, would it be better to use a different valve before the regulator, downstream before testing pressure is 100 psi, so we're reducing from 3,600 to 100.
Yeah, if you're a shutoff valve before a regulator doesn't necessarily need to be a ball valve. It can be a shutoff needle valve. And that allows you to open a little bit more slowly and not just slam the regulator with high inlet pressure immediately.
Okay. Perfect. Is there any other questions that anybody has?
And James, if questions do come up over the rest of today or the next couple of days, if they want to email them in, I'd be happy to address them. Maybe we can collect some of them over the next couple of days and then post a list of them on the website and have people kind of reference that for answers and stuff.
Okay. We do have one here, just came in. Here, where do we stand in regards to the competitive products such as TESCOM in regards to quality and product variety?
So the question was on quality and product variety. Is that correct? Did I hear that right, James?
Sorry, yeah, they're just wondering how we compare to TESCOM in regards to quality and product variety.
Okay, all right, good. All of Swagelok products we feel are very high quality. So I think from that standpoint, we're very competitive with our competition. From a variety standpoint, we do have a broad range of products available. Everything we talked about today, from spring-loaded to dome-loaded to a combination loading, we do have available. TESCOM does have some subatmospheric products in the larger sizes that we currently do not have. But other than that, we do have a pretty broad mix that is pretty directly competitive with our offering.
Looks like that's about it for questions. I just want to let everybody know that we do have a website for the Canadian Western area for regulators, as you'll see on the screen there. On that website, you'll see information when it comes to selecting regulators, packaging documents, whether you want to do any maintenance or repairs. It has all of our certifications for our regulators, for example, CRNs and things like that. And it also has upcoming events that we have in your local areas. The other thing you'll also see on the webpage, on the homepage, is what you'll also see here on the screen is our local contact numbers for all your local distributors. As a bonus today, as everybody that has attended, we will be sending out and getting in contact with you and getting everybody one of our new regulator reference guides. It's something that it's new in creation, and we'd like to get one to everybody that participated today. So I just wanted to say thank you very much for taking your time today and attending this webinar. And again, if you have any questions for Eric or from your sales reps or anything, please feel free to email them in, and we'll make sure we contact all of them for you. So thanks again for today, and we'll be signing off the meeting now. Thank you very much for your time.